From this video, we'll start looking at the Laplace transform. Laplace transform can be written down as capital F as a function of S, which equals to LF. L is the Laplace transform. The lowercase f is the function you want to transform. Mathematically, Laplace transform can be written down as integrate from 0 to infinity e to the power of minus st multiplied by ft, then dt. You may have also heard of Fourier transform. Fourier transform can be written down as capital F W equals to f small f. The first f is Fourier transform. The second lowercase f is the original function, which equals to 1 over square root 2 pi, then integrate from minus infinity to infinity, then e to the power of minus I wt, then fx. And this is the Fourier transform. I hope you can see some similarities between the Laplace transform and the Fourier transform. The main difference is in the Laplace transform, it's e to the power of minus st, but in the Fourier transform, it's e to the power of minus I wt. In fact, Laplace transform and the Fourier transform are related. We'll make a separate video to discuss this in the future. Coming back to the Laplace transform, if we have the capital Fs, we can apply inverse Laplace transform to obtain lowercase ft. Let's look at one example here. You know after Laplace transform, you get the expression 3s minus 137 over s squared plus 2s plus 401. And we want to know the expression before Laplace transform. Then what we need to do is to consult with the Laplace transform table. For the expressions on the left, these are the equations before Laplace transform, and the ones on the right, these are after Laplace transform. What we need to do is to convert our expression in this question to something that we can use in this table and calculate ft. F here is the lowercase f. Coming back to the example, we need to apply inverse Laplace transform to the expression to get ft. One trick we can do here is to treat s plus 1 as one term for both the numerator and the denominator. We then can break down this single term into two separate inverse Laplace transform terms. Notice you can write 400 as 20 square and take 7 out from the second part of the expression. You can have 20 left in the numerator. From the table you have seen just now, you know if you apply inverse Laplace transform to e to the power at cos omega t, it will give you s minus a over s minus a squared plus omega squared. Similarly, if you apply the inverse Laplace transform to e to the power at sine omega t, you will get omega over s minus a squared plus omega squared. Let's look at the expression above. In both cases, a is equal to minus 1 and omega is 20. Then we can write down the original form of the equation. It is quite straightforward and I will not read them out for you. You may wonder why we bother learning Laplace transform. How is this going to help us with solving the ordinary differential equations? That's something we're going to discuss in the next video.